This is Hussein Shakani from Learn Piezo. Today we're going to speak about an important topic, and that is the anti-resonance-resonance relationship with the coupling factor. I'm sure many of you who have been in the piezo characterization space have definitely noticed that, well, we usually calculate this coupling factor effective. And we also calculate coupling factors for the K33, for example, and KP and K31 modes, and they don't have the same equation as the K effective. What's happening here? We're going to break it down for you here on this video from Learn Piezo. But before we do that, let's just give a quick plug. I perform and do consulting services in ultrasonic device product development. So check out my website, ultrasonicadvisors.com, for the information, and also sign up for my email list. So the coupling factor. We described in another video that I'll link the coupling factor K effective, or just plain, let's just call it K squared, and don't necessarily ask me why we square this thing, is equal to the input mechanical energy, or the input energy of your crystal, and we have on the top the converted energy. So what I mean is that we put in, like, you have your piezo crystal, and you apply a voltage. That's your input energy, 1/2 C, which is the capacitance, voltage squared. That's your energy in. And the output energy is then your strain. So you have, so you'll have your effective spring constant, which is related to the geometry and your piezoelectric compliance, followed by the displacement I'll call delta L, for lack of a better term, squared. So we have some equivalent parameters. Basically, your piezo changes shape. It gets to be maybe longer depending on how you apply your electric field, and therefore you get this conversion. So you input a certain amount of energy, and some of it gets converted. And in reality, there's some of it stored in pure electrical, some of it stored in pure mechanical. But as we observe it, we input a certain amount of energy. In this case, it's electrical, and we convert a certain amount. In this case, we have an equivalent spring constant of our system, along with the length squared, which is kind of just a way to lump these parameters together. Just like we would do electrically like this, we'll do it mechanically like that. So I have several videos on Learn Piezo regarding coupling factor. So if you want to go into the basics, I recommend you go there first, learnpiezo.com. So now we're going to get back to the heart of the matter in the effective coupling factor. And for a moment now, cross out this idea of effective and just call it the coupling factor. So the coupling factor squared, and what's the relationship with the impedance, or admittance for that matter. So you have your resonant frequency, I'm going to call it anti-resonance, I'm going to call it FA, and resonance I'm going to call it FR. Some people call this A and this one B. That's fine. So we'll continue. So what's the relationship with these 2 points with the coupling factor? And to get into discussing this in detail, we have to understand why these two occur. And to understand why they occur, we're going to look at the equivalent circuit of the piezo. And the reason why we look at an equivalent circuit instead of, it's not EQ, it's EC, instead of an equivalent mechanical model, because we know, just like, for example, there's an LCR circuit governing a mechanical model, an electrical model, and a mechanical model will have, your mass spring damper. So why would we use our electrical model rather than using a mechanical one? The reason is the mechanical model can only model the mechanical phenomenon, whereas the electrical model can contain both a mechanical and an electrical response. And this is exactly what happens here. You have a mechanical response at resonance, and I'm talking in general terms, there are caveats here, and a electromechanical, you could say, response, having to do both with the intrinsic capacitance of your transducer or piezo ceramic, and your mechanical response arising from resonance. So let's get into that detail. So right now we're going to be talking about the equivalent circuit in terms of coupling factor. So we have here our piezo circuit, and this circuit modeled will create that quintessential resonance, anti-resonance, and then drop back down. This circuit creates that. There are also other circuits which can do it, but this is the most elemental and simple. Analyzes the transducer by itself, so it's I love to use it for analysis and explanation. So here, as we've talked about in other places, this is the mechanical branch. Basically, when the piezo, that response to the resonance, so you have the capacitor and you have the inductor and resonance, and when that occurs, you have this decrease in impedance. Otherwise, at off resonant frequencies, you essentially just have two capacitors in series. This inductor is not active, and the resistance is quite small. Off resonance, these capacitors dominate the response. Therefore, your piezo will behave like a capacitor, and you can measure things like the permittivity under constant stress. However, we are talking about coupling factor. So let's continue with that. So your equivalent circuit, if you're only going to simulate this part, let me just change my color here for some brightness. Oh, that's much brighter. So we'll have, if we just simulate this part of the circuit, you would have your capacitance at off resonance, then your resonance response, and then it would continue back up and down. So this dotted line right here, and that is just your capacitor. And this area right here is when it all gets into resonance. And this is, you could say, similar to a mechanical response, where you have about just a plane. You have basically a static or a constant amplitude response until you get your resonance, and you peak and you come back down. That's your mechanical resonator, and eventually your displacement will go to zero as your frequency goes to infinity. Erasing all of this, I'll just erase that. So when we add this other capacitor here to the mix, what we end up getting is, as you can see, what's missing from here, you end up getting that second peak. Well, you end up getting that second feature, which is known as the anti-resonance. And in this case, both of these resistors, both of these capacitors are resonating, you could say, against each other, such that at this frequency, your LCR circuit, which is now past the resonant point, has a response, and this capacitor also gives its response, which is opposite. So where these actually these circuits cancel out in frequency the most, or sorry, in current the most, that's where the impedance is the highest. The lowest current, highest impedance. This is destructive interference. And the frequency where this destructive interference is the highest, that is the anti-resonance impedance point. So as you can see here, the resonance frequency, that's a mechanical phenomenon. That's an LCR. And then we have the anti-resonance, that is a electromechanical phenomenon, or you could say a mechanical capacitive phenomenon if you wanted to be more creative with your terminology. You have an LCR and you have a C, and that's how you get this point here. And you have the destructive interference between the two, and therefore you get the highest impedance. So great, we explained why this capacitance here. Before resonance, before the resonant frequency, the capacitance is related to both capacitors in parallel, but afterwards it's only this capacitor here. Because this part gets phased out. As you increase way past your resonant point, your current starts to dip, and that the current decreases, or in the mechanical phenomenon, as we can understand, the mechanical vibration way higher than the resonant frequency starts to approach zero as your frequency starts to increase. Even higher and higher, but however, in a real system, there are several resonant frequencies, so that never really happens. So again, we explained why this occurs, but how does this all relate to resonance and anti-resonance and the coupling factor? So let's take a look at this. We have this, which is the mechanical. So this is the pure electrical, and we'll just call this the mechanical part. This is often called C0, and this might be called C1, or vice versa. Actually, maybe not, but something like this. So these different terminologies. Sometimes they're just called C and C1. However you want to go about it, it's fine with me as long as you know what I'm talking about. So this is actually, if you think about it, this is actually a capacitor. And if you recall earlier, I had that equation, 1/2 QV squared. Right? And here, although the voltage is not known because there's a inductor after it, so that's going to affect the voltage across this capacitor, but you could say the same thing. Sorry, 1/2 CV squared. My bad. And you could say the same thing here. 1/2 CVO. I'll just call this N squared. So it has its own stored energy in this system. So these are essentially two energy storage components. One of the energy storage components relates to mechanical energy, and that's the bottom branch. And the other energy component, the capacitor, not to dot in parallel, that relates to electrically stored energy. And both of these, and this one relates to, you could say, the resonant frequency, and this one, you could say, relates to both resonance and anti-resonance. And you could also say the same for the coupling factor, and I mentioned K squared, and that's the converted energy on the top and the input energy on the bottom. So if your input is electrical and your output is mechanical, you start to create the notion that, hey, maybe they're actually related, and perhaps I can back out these components if I know the coupling factor, or there could be some relationship between the resonance and anti-resonance frequency that would lead us to calculation of these parameters. So here are some equations now that are going to be familiar to you. So we calculated the effective coupling factor squared as being equal to the square root of the anti-resonance frequency squared minus the resonant frequency squared divided by the anti-resonant frequency squared. And I made it kind of simple. Cancel that. So I made an analogy that's just 1 over 1 minus x squared, whereas x is equal to fr over fa. That makes for easier calculation if you're interested in doing that. It's also from the circuit analysis we can conclude, and if you do, if you solve the equivalent circuit at the LCR circuit and you solve for the resonant and anti-resonant frequencies, you can get this equation to look like this. Equal C1 over C0 plus C1. So this is the, if you can remember, or let me just make that correction right here. So this is C, and I called, and C plus C, and we would say, with this definition, I think I described it a little differently before with regards to the terminology. So this is C1, and this is C0, and then we have our LCR. So they end up, you can actually relate the resonance and anti-resonant frequencies to the LCR C circuit, also known as the Butterworth Van Dyke circuit, and therefore you can actually come up with the relationship. So the coupling factor is related to the equivalent circuit components as well as the resonance and anti-resonant frequencies. So we measure it using the resonance and anti-resonant frequency, we report it, and that's how all of this becomes related. And you do know that this parameter squared is then the actual coupling factor. For some reason that I actually am not aware of, we typically use, I forget why, we typically report the coupling factor not squared, but in actuality it is actually squared if you wanted to refer to the converted energy over the input energy. So, going forward, and you can probably find the answer to that. I forget right now. You can probably find the answer to that in the other one of my other videos on the coupling factor. So going forward now, with regards to like K33 and K31 and KP, the radio mode, we have all of these equations. The radio mode has to do with the Bessel function, so we have complex sinusoidal kind of long equations to come up with these parameters from the resonance and from the anti-resonance. They're much longer and much more complicated. The reason why these parameters are longer and complicated is because they correlate and they go back to calculation of the kind of the essential definitions using base material properties. So the purpose of calculating these is then to get to a base material property that would be observed under ideal applied electrical and mechanical conditions. So we have our K33 squared defined as D33 squared divided by the permittivity of free stress times the elastic compliance. And now in order to get this from a impedance curve, it has to go through many sinusoidal transformations and ratios between the resonance and anti-resonance frequency in order to back this number out. And the same with the K31, the same with the KP. It requires a much more intense analysis and derivation in order to come up with those ratios and parameters in order to get this simple result. So as for your next steps here, we basically prove that the resonance and anti-resonance frequencies relate to the coupling factor, and that effective coupling factor for a specific resonant mode. And that's has to do with how they relate to the LCR circuit and the parallel capacitor. And we also described why things like the K33, the coupling factor in the 3.3 resonator, and the coupling factor for KP and K31, and actually for that matter KT, will be more complex because they actually end up defining basic material properties instead of a equivalent circuit approach to looking at the whole system. So, with that, if you have any questions, feel free to reach out to me. You can go in the description and sign up for my email list. You can visit me at learnpiezo.com. Also, ultrasonicadvisors.com, which is my consulting platform. And also feel free to look around for more videos on this topic and let me know if you have any questions and what you think about this video. Thank you.